So this is the MBQC session. So if you want to see contextuality, you need to run away now. First up, we have Filipa Perez talking about quantum circuit compilation and hybrid computation using Pauli-based computation.
Thank you for the introduction. First of all, I ask for your patience. I'm going to keep my mask on, but if anyone's having trouble understanding or hearing, let me know. Maybe I can speak up a little or approach the mic. I don't know. And second, I want to thank the organization for putting together this amazing conference. It has been an awesome experience. So this is only my the second year of my PhD. So this is my first big international conference, and speaking here is very exciting. So I can't wait to show you what we've been working on. So let's just start with a brief presentation overview. I'm gonna start with some motivation and preliminary concepts, but I'm gonna fly by this because most of it has either already been talked or I think most of you will be familiar with. And then we get into the really juicy stuff, which is Pauli-based computation. And since this is the MBQC session, I think it will come as no surprise that this is an MBQC model. And then I will show you how to use this model to perform circuit compilation. And finally, I will address hybrid computation, and I'll comment a little bit more about this term hybrid that I'm using in due time. So just as a brief motivation, as you know, current quantum hardware is sort of limited in its capabilities, and so we aren't quite ready to or quite able to achieve quantum advantage with current devices for practical applications. And this is why hybrid techniques have sort of gained some traction recently. And most of you will have heard about variational quantum algorithms such as VQE and QAOA. And this is sort of where my work fits in. So focus on hybrid techniques for quantum classical computation. Okay, now let's fly by this. I'll talk a lot about Pauli operators, and these are just tensor products of single qubit Paulis, X, Y, and Z. The Pauli group has two N generators, which you can write as X and Z operators. And then there's the Clifford group, and Clifford unitaries are just unitaries that map Paulis into Paulis under conjugation, and you can do this efficiently. And for instance, you can show how the generators of the Pauli group are mapped under conjugation by the generators of the Clifford group. So for instance, the Hadamard maps X into Z and Z into X, and you can do the same for the phase gate and for the C0, which are the other two generators for the Clifford group. And we also know that if we introduce any non-Clifford gate, then we unlock universal quantum computation. And in particular, in this presentation, I'll talk a lot about the T gate. And the final concept is just the concept of magic state injection. And in particular, I'll talk a little bit about the A state. I apologize for the image, I couldn't resist. Then I'm sure most of you will be familiar with this idea that if you have a T gate, you can just replace it by this well-known T gadget, where you bring in a resource state, which is a magic state, and you just have Clifford gates, and you need classical feed-forward to determine whether or not you apply an S gate or not. And then you will have enacted a transformation that's basically a T gate on the main qubit. And this concludes everything that you'll need to know to follow this presentation. So let's get into the interesting part. So in 2016, Bravi, Smith, and Smolin published this paper here, where there's a theorem that says that if you have a Clifford plus T circuit with n input qubits, T gates, and a certain number of final Z measurements, you can simulate this by what they call the Pauli-based computation. Here I call it that calligraphic Q. And what's the structure of this Pauli-based computation? Basically, you have as input a product state of magic states, but you have T qubits. So you don't have N qubits anymore, you have T, where T is the number of T gates in your original circuit, okay? And then what are the operations? Well, again, this is the MBQC session, so the operations are measurements. But what kind of measurements? These are measurements of t-qubit Pauli operators. And I will prove that these are at most t measurements of Pauli operators. And moreover, these operators are pairwise commuting and are independent. Okay, so this is the structure of this Pauli-based computation. And I'm going to try to convince you in a visual way that this is true very, very quickly. Okay, so step one, we have our quantum circuit, our Clifford plus T circuit with a certain number of final measurements. First step is use the T gadget that I introduced before, and we transform every T gate into a T gadget. So now we have an adaptive Clifford circuit, and we have T intermediate measurements hidden somewhere inside that circuit. Okay, this is step one. Step two. Step two is use the other concept that I introduced, which is this idea that you can conjugate Paulis by Cliffords in an efficient way. And so you take the measurement that you have from the first gadget and you push it to the very beginning of the circuit, and it will show up in the beginning as a Pauli operator on n plus t qubits. And this is P1 prime that I called here. Okay, so you just push it to the very beginning. And now in principle, you would have to measure this operator. That's not what we're going to do yet. So what we do now is we have this operator at the beginning, and we just insert some dummy operators that are basically Z operators acting on the qubits of the stabilizer register. These do nothing, right? So it's just Z on 0. And now we realize that there are two options. So this Pauli that has just shown up here either anti-commutes with previous Paulis. And if it anti-commutes with previously measured Paulis, then it's easy to understand that the probability of getting 0 and 1 is just 50-50. And so instead of measuring, we can just make a coin toss to find out what the outcome of the measurement would be. So we do that. We make a coin toss and find out what the outcome is, and we just drop the Pauli. We don't need to measure it in our quantum hardware. And instead, put a Clifford unitary in its place, which is the unitary that prepares the state that we would have gotten had we done the measurement, right? Because we need to prepare the correct state. And the point is that this unitary is Clifford. That's an important point because it doesn't ruin the propagation of everything else that we'll need to propagate after this. There's a second option, and the second option is that the Pauli commutes with everything that has come before. And if that's the case, then we have again options. The first option is that it depends on previously measured Paulis. And if it depends on previously measured Paulis, then we know the outcome, or we can determine it classically. And so again, we don't need to do the measurement in the quantum hardware, we can just determine it classically. And then there's the final part, which is that it can commute and be independent. And that's when we need our quantum hardware. That's when we actually need to do the measurement, because it's not trivial what happens then. But I promised you that you would have to measure only things on the magic register, right? And here you have this big Pauli. But the point is that if it commutes with all previous operators, it's necessarily trivial on the stabilizer register. It's either identity or Z, and you can just drop what happens there. And so you can just, in your quantum hardware, measure P1, where P1 is just the bottom part of the Pauli. And then you do this for all the measurements that you have in your quantum circuit. This is just the example for the first. And some will be classically dealt with, and some you'll have to measure, and another measurement will show up, and so on. And this is how you do the computation. Okay. Right, so this hopefully convinced you that you can simulate any Clifford plus T circuit in this way. And now I think most people are familiar with quantum circuits, not this. This can be sort of confusing. And so what we thought was, how can we map this back to circuits now that we have something that has this structure? And in 2019, there's this paper here whose main goal is not this one at all, but they have a theorem in there that they call the extended Gottesman-Neal theorem, which is basically this idea that if you have an adaptive circuit like the one you see on the left, you can just transform it into an adaptive circuit like the one you see on the right, where you just have the magic register. And they explain this in light of what I just showed you, that you can go to PBC, reduce this to something that acts only on the magic part, and then come back to circuit. And they mentioned, this is not the main goal of the paper, so this is just mentioned, that you can do this with T cubed over log T operations. And so the first thing we did in our work was find a different way, and maybe I'll argue, maybe arguably more intuitive, but at least I think it's more intuitive, to kind of open these black boxes, how to do these Pauli measurements. And we propose something like this. So we have a certain Pauli operator that's just a tensor product of single qubit Paulis. And the way to measure such an operator is just, we need to bring in an auxiliary qubit in the plus state, and then just do controlled operations on the appropriate main qubits, and then measure, and so on. So this is how we propose to do this comeback to circuits. And if you do this, you need order T-squared operations and also depth. And so we took this a step further, and we wanted to illustrate that this actually works and that we can get interesting results with this. And so we wrote Python code to do this, and now I'm going to show you some results. So the first circuits that we used are hidden shift circuits. So are kind of neat because they're deterministic. We know what the outcome is, so we can test that everything is working okay. And here you see what we call classical runtime per shot. Okay, so what's this time? This is basically the time the time it takes you to do all the classical processing associated with this procedure that I just explained to you. And you will notice that while you're so we call this the compilation, while you're compiling, you're also already simulating the main qubit, because you're already deciding the first measurement is 0, the other one is 1. So the two processes, you cannot separate them. They're completely interleaved, and there's no way of separating the two. So this is the time of each compilation or weak simulation or whatever you want to call it. So you see that it's of the order of the hundreds milliseconds, which is not great, but it's Python code, so could be much better if someone else wants to implement this in a different language or something. But now the really interesting thing, so I'm not so much worried about the classical time, but the features and how they change. So, and here you can see the depth, and in particular in green you see the depth of the original circuits, hidden shift, and the x-axis is the number of qubits in the original circuit, and in this case the T count is fixed to 14. Okay, so, and what you see in orange or yellow or whatever that color is we tried to do some pre-compilation with some Qiskit tools, and you see that there's some reduction. But then what you see is that our what we call PBC compiled circuits have a depth that's much lower than the original ones, and we were quite happy with this result. And you can make similar plots for a single qubit gate count, and again you can see a great drop from the original circuits to the PBC compiled ones, and the same for the CNOT count. Okay, but this is for hidden shift circuits, and then we decided to do the same for random quantum circuits, and again you see that the time is more or less the same order of magnitude. And here for complementarity, we fixed the number of qubits in the original circuit to 25, and instead varied the T count. So here, notice that the x-axis has changed, and now it's the T count. And you will see something a little different. So now the original circuits again are in green, but you see that our PBC compiled circuits kind of become deeper, around 10 T gates. But yeah, I could have if I wanted, manipulated the position of the green crosses, because I could have just added more layers without adding more T gates, and that would go up or down. So this is, you can take this with a grain of salt. So, and here the single qubit gate count, you can see that although the depth is larger, we still have fewer gates. And similar with the CNOT, although in 22 you can see that we already looks like if we had continued, we would have more T counts than more CNOT counts than the original circuit. Okay, and now I just want to go to the last part, which is this task 2 that I called hybrid computation, and I promised to comment a little bit about this term hybrid. And this is important, which is the following. I think you will agree that this first task that I already talked to you about is already hybrid in the sense that we are already using the classical computer to do part of the processing, and we are already offloading some of the cost to a classical machine. So here the term hybrid is used in a slightly different way, and is in the sense that you have a computation on n plus k qubits, but your hardware only has n qubits. And how can we sort of get rid of these qubits, these k qubits that we have too many? And this is sort of natural in Pauli-based computation. It's very, very easy to do. And the idea is we have a big Pauli-based computation that, again, I call Q. And now the task is going to be slightly different. So we want, for instance, to get the probability of getting the outcome 1, of measuring the outcome 1. So, for instance, we want to solve a decision problem or something like that, and we want to have an estimate for this probability. And we have n plus k qubits, but we need to get rid of the top ones that I marked red. And so what we do this is we kind of decompose the magic state into stabilizer states. And it will be something that looks like this. And because these are stabilizer states, you can always produce them from the ground state using a Clifford unitary, which I call U sub I. And now what you have is basically you have decomposed your large Pauli-based computation Q into M. So the sum was, the sum was in M. So you have decomposed it into M different Pauli-based computations that now have the 0 state on the first k qubits. And similar to what we saw in the beginning of this presentation, you will sort of be able to get rid of what happens in the stabilizer register. And you only have to measure the operators in the bottom part. And so you have sort of naturally got rid of the k qubits that you had that didn't fit in your quantum hardware. And basically you can define some unbiased estimators for the probability of the small Pauli-based computations giving 1. And this is just that B sub I, which is the outcome of the Pauli-based computation, either 0 or 1. And you can show that this is an unbiased estimator for the probability. And then by linearity, basically the probability of the big Pauli-based computation is just a summing with the appropriate weights. And again, we coded this. And here, again, the results first for hidden shift. And we knew so here you can see the bit string that we were supposed to get. And hopefully you can see that there's some magenta diamonds that always get the correct result. And this was for a precision of 0.1. You can see some green confidence intervals here. And for 1 virtual qubit, we did the same for 2 virtual qubits, 3, 4. And the results were always the ones that we would expect. And then we did the same for random quantum circuits. Here, instead of changing the number of virtual qubits, I just chose to show you what happens if you have, if you choose different precisions, and it's just the confidence interval gets narrower. Okay. And yeah, so to conclude, basically, I think that what I hope you got from this is that this Pauli-based computation seems to be a promising tool in terms of circuit compilation and hybrid computation. And if you're curious about this, you can check out the archive or the code that we shared on GitHub, or you can corner me in the lunch break or the coffee break. I'm easy to spot. I'm the alien in the green mask, basically. And yeah, I think that's it. And I'm happy to take questions. Thank you.
Okay, any questions? Yeah.
So I think you had a slide somewhere directly comparing sort of your compilation to what Qiskit would do naturally.
Yeah, I just I just did some. It was not very advanced stuff. I just used the transpiler and asked it to sort of try to minimize some gates and stuff like that, and he did. Oops, sorry, I already went too far. And he did give me the yellow things. But like maybe their tool could work a little better. I didn't try to like really hone it very deeply, but yeah, I just used their transpiler, and I told it that it should use the same gate set, like it was forbidden from changing gates or something like that, because that would be an unfair comparison. And that's what Qiskit gave me. But this was just, instead of Qiskit, we could have used something different.
Yeah, sure. And Qiskit does have certain limitations. It's doing the best optimizing routines. But I was just wondering, sort of, is this sort of, because you're using different operations, like you're using a lot of measurement in the circuit, right? So is this a sort of direct
So what's in the end, what we have are circuits that look like this. So you have measurements inside the circuit. Yeah, the auxiliary qubit, you have to measure it to get the outcome of each Pauli, and then you reset it. Of course, you could have just had more auxiliary qubits and measure each and have them die after the measurement, but that's not very useful, or you're increasing the number of qubits unnecessarily. But this is basically how our circuits look like. So these are just control gates and Hadamards, and that's it.
Plus the measurements at the end.
Plus the measurements after it, yeah.
And are you counting those as gates in those plots, or?
Good question. I don't remember, but in this plot, even if there aren't any measurements, you would raise the dots by 14, because that's the number of measurements at most that you have, and 14 is nothing in this kind of scale. So, but yeah, I don't recall if I counted the measurements as gates. I would have to check.
Yeah, the measurements can be expensive themselves in current hardware, but
yeah, sure. But in terms of just counting here, it would just be raising this by 14 each.
For sure.
Have you considered combining your techniques with ones for T-count reduction? Because presumably that's kind of another optimization that would work well here.
Yeah, so because of that, I kind of started reading all the ZX calculus papers. And yeah, there's this one paper that specifically addresses this. And so that would be an interesting thing, like start first with something like that reduces the T-count, and then doing this, because then it will drop the things even more, because the lower the T-count, the better. But yeah, that's something that makes sense to do, no doubt.
What does the dashed red line mean here?
Okay, so we derived some upper bounds for the depth and the gate counts in our paper, and these are basically the deeper circuits you could have, and this assumes that all your Paulis are non-trivial, so they never have identities in your Paulis, and so these are really gross overestimates. And here in this graphics, you just see that very clearly. Like you're assuming that all Paulis are non-trivial, and you always have identities, and so yeah, that's what you're seeing there. And here it's horizontal because the T count is constant here. I told you it was 14, and in the random quantum circuits you see that it's T squared, so it goes with T squared. So that's why you have here the parabola, and yeah, okay.
Yeah, have you thought about the problem of extracting a unitary circuit from a PPC to go fully back to a circuit with no internal measurements?
No, we didn't think about that. Yeah, that's something that we could think about. I'm not sure how it would work, because you kind of need, as soon as you put the T gadgets in and you start propagating things, you kind of need the outcome of this one to get the other Pauli. But so I'm not sure how that would work, but that's something we could maybe think about. But I'm not sure how it could, or whether it could even be possible or not.
Thanks. Okay, let's move on. Thank the speaker again.